Welcome to the first webinar of the year, which is a series of webinars. We are planning nearly 24 webinars coming, and we will publish each and every topic in our Facebook sites and the WhatsApp pages. So the purpose of this webinar series is to give knowledge to our members and the technologists in our industry. So there will be a lot of interesting topics coming in. And first of all, I must thank Dr. Suranga Rajapaksha, who is heading the project as the chairman of this subgroup, for his efforts. And within a very short period of time, he was able to get good topics line up. And I think from tomorrow onwards, you will be able to see in our websites and also in social media what are the uh, subjects we have line up. And also, after listen to this one, we will publish this series of webinars in our YouTube channel. So you can refer this. And this is a very valuable set of webinars what we are planning. Apart from this, there will be some workshops coming in with regard to these topics later on, and we will publish that one also. So I think without further ado, I would like to invite Dr. Suranga Rajapaksha to take over from here. Doctor.
Thank you, Mr. Chairman. Today it's very valuable time for me because we are starting new series of webinar for this year. So this is the first webinar, and I would like to introduce today's speaker, Dr. Gayan Sirivardhana. Today, we have selected this topic considering new trends in industry, and I think in Sri Lanka we should be in the front of new technology. As a result of that, I have invited this speaker, Dr. Sirivardhana, because he is the one of the experts in this field. Dr. Sirivardhana completed his PhD and master's in United States, and his specialties are polymer chemistry and polymer additive manufacturing. He earned his PhD from University of Texas, Dallas, where he was actively involved in advanced 3D printing and additive manufacturing research. He has published many first author research papers related to this additive manufacturing. During his postdoc research at Virginia Tech, he has collaborated renowned research team related to 3D printing and additive manufacturing. It is my pleasure and I'm humbled to introduce today's speaker. Please warmly welcome Dr. Gayan Sirivardhana for today's seminar topic 3D and 4D manufacturing. Dr. Sirivardhana, thank you so much accepting our invitation and supporting our project. So we are trying to create new generation of industries in Sri Lanka, and your knowledge is very valuable for us. And during our webinar series, if anyone has a question, they can raise your hand, and then we can direct the question to the speaker, or we can wait until our speaker complete his session, then we can have a question and answer session. Dr. Sirivardhana, over to you.
Thank you very much, Dr. Suranga. So hope I am audible.
Yes, we can hear you. Yeah.
Thank you very much once again for your kind introduction. And first of all, I would like to thank PRI, Professor Nilmini and Dr. Suranga again for giving me this opportunity. I really appreciate it, and I look forward to do a good job as far as I could. Let me share the slides with you. Right. Hope you can see the slides.
Dr. Sirada, your mic is muted. Yeah.
Okay, can you all see the slides?
Yes, yes, you can. Yeah.
Okay, all right. So, right. So, again, thank you, PRI, Dr. Suranga Ilmini, for giving me this wonderful opportunity. Right. So, today I'll walk you through 3D and 4D printing of biomedical materials. Right. Trends, challenges, and future overview. Right. So, time I have is like 1 hour, so I'll try my best to do a good job as far as I could. Right. So, so since the topic gives you a kind of thing called 3D and 4D printing, right? So, and it basically, as the topic implies, it should cover biomedical materials. But so, since there are maybe some members in the, the participants list that has a low knowledge about 3D and 4D printing, right? So let me first walk you through what is 3D printing first, right? And then the technologies available for 3D printing, and then I will move to 4D printing, and then introducing examples of biomedical materials in both 3D and 4D, right? Fabricated, right? Does that sound good, Dr. Suranga? The plan I have?
Yeah, yeah, that's good. Yeah.
Sure, thank you. Right, so right, so what is 3D printing? First, this is actually first of all the 3 dimension 3D, that is, right? You have to have a height, right, and width and length for a three-dimensional object. So that is the actual meaning of 3D. So you will end up with fabricating a 3-dimensional object which has a width, a length, and a height, right, or a thickness. Right? So it's a layer by layer manufacturing process. Right? So you lay the material layer after layer, right, on a print bed. Right. So first of all, again, I have to emphasize why we are interested in 3D printing rather than conventional, molding techniques, is because of the ability of 3D printing, or we call it additive manufacturing, to manufacture complex shapes, right? So that cannot easily attain via conventional molding techniques, right? So you know that if you go to, conventional molding techniques, you have to make a costly mold, right? Usually stainless steel in most of the cases, right? And right, so you have to pay a lot cost, right? You have to pay a cost for that, and also, right? So this 3D printing, right? So you can come up with many uh, complex shapes, complex structures, right? Just by changing the pattern of the nozzle, right? The printing pattern or the laser tracing pattern, right? On the printing object, right? So complex getting or obtaining complex shapes, right? That is the main advantage of doing 3D printing. So which you can apply in dentistry, medical fields, in any like high surface area related materials for filtration process, and like variety of myriad of applications, right? Wide range of materials and techniques available, right? So I will go through that. Here, I just wanted to show the history of the origin of this one. So around early 1980s, the company called Stratasys laid the foundation for this technique, right? And then actually you can see through the slide, mid 80s and late 80s, it went through some commercial. So SLA means stereolithography, right? Printing patents and related stuff, and then selective laser sintering, SLS patent came around 1988. So this filament-based fabrication is also called FDM. So they patented the first one in early 90s, and then you can see the jetting, right? Binder jetting, this is called BJ, binder jetting, and then bioprinter-based development, right? So you can see after around 2000, early 2000, right? So they have tested 3D printing of blood vessels, right? So that's a advantage for biomedical right industry. So the initial initial research efforts came around to early 2000, right? So, and then it's developing. You can see first FDA approved 3D printed tablets also came up around 2015, right? So this is getting progressed, right? So this is the origin of 3D printing and progress. And then actually 4D printing started around 2020, that kind of era, right? Even involvement of 4D printing and so on, right? So this is just wanted to show you the origin and the progression. By the types of 3D printing, that now this slide shows you there are many 3D printing techniques available, right? So our main topic is 3D and 4D printing of biomedical materials. So printing of biomedical materials also can be categorized via printing by extrusion-based methods and also by laser sintering, right, and energy deposition and so on, right? So that is why I will go through these techniques little by little and then come to that biomedical section, right? So you can see material extrusion at the top. So that is the most widely used, right? And even in Sri Lanka, this is the one we have currently in most of the cases, right? So this the you can see there are two, FFF and DIW, right? So FFF means fused filament fabrication. That's our usual filament-based printing, right? And DIW is the direct ink write. Okay, so again, I will walk you through these things in next slides. So these are the two main extrusion-based 3D printing, right? So what you do is basically you deposit the material on the print bed, either as a filament or through a syringe, right? Through a syringe, that is the direct ink write, right? So if you use a filament through a nozzle, right, that's fused filament fabrication, right? So apart from that, you can see the right-hand side, wet photopolymerization. So if you need high resolution, right? So this is little bit high costly material-wise and also equipment-wise. Right, so you can see wet photopolymerization again divides into several techniques. Stereolithography, that's SLA, and digital light sintering, DLS, and digital light projection, DLP. Right, so you can see curing, right? So here, what you basically do is you get the material to a vat or a bath, right? That's usually a resin, and then you use a laser, right, or UV, right? UV laser usually to cure the material through a trace patterns, right? That is how the mechanism there is. Again, layer by layer fabrication of material on a print bed. Then you can see in the top left powder bed fusion. So I am talking in terms of the priorities or the important wise, the mostly used wise, right? Material extrusion mainly, then wet photopolymerization and powder bed fusion. So right, so extrusion usually goes through thermoplastic materials where wet photopolymerization, photo-curable resins or polymers, right? And in terms of powder bed fusion, right? So people can say, can you only print polymers, right? No, you can also print ceramic materials. So that is through powder bed fusion, right? Ceramic materials and also metal powders, okay? Powders, so you can see that's the technique to be used for such kind of materials like powder form. Again, you can see you can fuse with laser or heat or high electron beam, right? So there are several techniques here also available: selective laser sintering, SLS, selective laser melting, selective heat sintering, electron beam melting, um, right, masked light DMLS, or we also call that direct light projection, right? So I will go through those things. You can see the curing mechanism is little bit different. That is how these sub techniques arise. Then you can see the jetting techniques, left hand and right hand middle. The left hand you can see binder jetting, and right hand you can see material jetting, right? Jetting like the droplets, right? So in binder jetting, you use a binder, right? Like the adhesive, right? To bind the materials, right? Together, right? Now in the powder bed fusion, you use a laser or a heat or high energy beam to fuse them together, the particles, the powder. Here you are using adhesive. In material jetting, again you drop, you use the jetting technique, and then simultaneously you usually use UV curing, right? A cure with UV light. That is how you end up with a rigid material. Every time, once you deposit the material, then you have to worry about the solidity, right? Or the structure-wise robustness, how the material would stand on the print bed, right? So you have the mechanisms for each and every technique here, which I will go through in future when I go through the future slides. You can see at the bottom another technique called directed energy deposition, right? High energy deposition, DED. There also you have several techniques, right? So that's DED also used with many printing of biomaterials, right? And you can see another one, sheet lamination. So, right, that's also another type of 3D printing, that like printing of paper and like film like structures, right? So when it comes to 3D or 4D printing of biomedical materials, many, like mostly the extrusion based types, right? And inkjet, like these jetting techniques and laser based techniques are widely available with the biomedical material printing. So that is our topic today. Right, so again, walking you through basic, like I will go through a little bit faster through these slides, just giving you up the basic intro, like for those who have little knowledge, right? FDM, so the extrusion, this is the black color is the filament, right? So you have many commercial filaments like PLA, ABS, right? PLA plus with some additives for, like easy for easy printing. And right, so many commercial materials available, right? And what you have to have is the thermoplasticity, right? So you have to have the material has to have the ability to melt once you heat the material, right? Inside this print head, we call this area print head, right? So you have to have an idea about the right melting point of the particular plastic or whatever the material you are using here, right? So let's say it's 100, then you have to heat the print head to 100 Celsius, right? Or closer to that to get it move through the head, right? Then you can see it melts and goes through the nozzle. And this blue one is the build platform. You also call that print bed, right? Print bed. And on the print bed, the material, you can see it deposits, right? It deposits. So how does the shape traces? So whatever the shape, let's say you have a like a face-like shape or a nose or whatever animal shape. So whatever the shape, you have to provide as a STL file, stereolithography. We call that .stl, right? So there are software like CAD software, like computer design, SolidWorks, and there are many other, right, like 3D modeling techniques. First, you have to build the model. Actually, now there are many, free materials are available in the website, like Thingiverse and so on. You can just download them and convert into a .stl form and directly feed the thing to the computer. The computer, right, connects with the machine here, and then that is how the nozzle gets the shape, right? So it supports, the software should support the nozzle to flow. So for an example, it's a shape of a bird, right? So the nozzle moves to the shape of the bird. I hope you can get the idea, right? So that's the first layer, and then you continually feed the material through these rollers at the top, right? So then the next layer, and so on. And what else you have to have the material here? Once deposited, it has to be solidified, right? So that is the thing called thermoplasticity, right? So you have to have that ability, right, to build up on the build platform, right? So you will end up with a nice 3D object via FDM. You can see plenty of materials, polylactic acid, PEG, that's polyethylene terephthalate glycol, and polypropylene, this is the ABS, acrylonitrile, butadiene, styrene, and so many commercial available copolymers and other. All these have to have the thermoplastic nature to be able to use FDM-based printing. You can see so many examples. Most of them I have downloaded through the actual research articles. Some of them actually I have cited the reference papers also here. So you can see many applications like electronic housing, right, day-to-day plastic toys and like household materials. You can see and some other ornaments like finger protecting devices and so on. Also, you can 3D print via this FDM, right? The other one is direct ink writing. So what is the difference here? You don't have to thermally heat here, right? Instead, what you do, you get the syringe here and you load the material, usually in the form of a hydrogel or a paste, right? So you all know about like toothpaste, right? Which we use in the morning. So that's that kind of how that the viscosity should be. That's the one example I gave you. Hydrogels, semi-solid materials, pastes, and so on, right? So you load the material here, and then you apply pressure from the top, right? Which you didn't see in FDM, right? So that's the difference, right? And then, through the nozzle, the material gets, printed again, layer by layer, right? That's again extrusion. So that's why it's also under extrusion, right? So a lot of biomaterial, bioprinting, right? So directly involved with our topic, biomedical printing, right? So bioprinting means you use this basically this DIW technique for that, because you can load whatever the cells, right, mixed with the hydrogel, right, living cells, right? You load it and you control due to control pressure, you deposit onto a substrate, and then usually you use a bioreactor, right, to and give time for the cellular growth and differentiation and tissue maturation. And then once everything is good, right, in vitro testing, then you can actually go for the in vivo, actually for the direct attachment into your body, right? So that's usually why people do DIW based bioprinting a whole lot, right? Then you can see hydrogels. These are the types of materials that you can process via DIW. Again, this is one of my own work in my PhD. So this is the hydrogel cups, right? And some structures with the inside complexity. So this is for like metal adsorption applications. And you can see again in like left bottom, you can see that's a civil engineering field also. DIW is used for fabrication of houses, not in Sri Lanka still, but in countries like France and European countries. You have to have large scale built up facilities and instrument and capital cost, right, for this kind of build up, right? This is 3D printing of concrete. You can see it's the concrete material. So this is DIW based printing, right? And you can see some other materials like ornaments, some other amusement parks and stuff. So all these are DIW based, actual research based papers I have taken, right? Right now, we'll switch our gears to another technique. That's the wet photopolymerization. Actually, I told you even in the second slide on that list. So this is the this is the technique where you use photocurable polymers, right? So you can see, so it's a resin usually in room temperature, these are resins, a lot of acrylic based materials are commercially available, right? So you have to have the photo curing ability, right? Such as in the thermoplasticity for DIW, right? For FDM, right? And the DIW, that's the you have to have the pseudoplasticity for DIW. So you apply pressure, the material needs to reduce the viscosity, right? That's the DIW mechanism. So here, the photocurability, right? So you can see several mechanisms based on the material, right? So here, right, as I told you, the material is the first polymer is there, and then here you use a laser beam, right? So laser beam that traces the pattern. Let's say again a complex shape. So the laser moves to that particular shape, and due to that laser movement, the material that particular section get cross-linked, right, and then gets hardened. Right, that's the first layer, right? So it continues, right, to the next one, and then you can see the layer by layer addition, right, to the until the end, right? So again, you end up with the layer by layer fabricated material. So again, the advantage here is the high resolution, right? Rather than using DIW or FDM. Here, because you use a laser, right? So you can end up with a highly like micrometer scale, high resolution printed objects. So the cost-wise, this is a little bit costly technique, but many biomedical materials are being printed, right? Again, this one is kind of like a little bit of high advantage, like a little advancement of SLA, I would say. This is digital light projection, right? Digital light projection, DLP. We also call that mass projection, wet photopolymerization, MPVP, right? So here, what you do is, I told you in the SLA, you use a laser. So like here also you can see laser. Rather than using laser, you use the lamp, right? Lights. But here what you do is you project an image of the material, and you can cure the entire layer at once rather than tracing the layer. Layer by layer tracing happens in the previous method where SLA, but here is a little bit high advanced. Why? Because the whole layer gets, now you can get the images, the material, the lens, you can see the digital micromirror device arrangement is there. You can get the image of the object to be printed, right? So those layers will be cured at once. So in terms of process-wise, it is more efficient, faster, right, than the SLA method. Again, many biomedical materials are being printed via this technique also, right? So as I told you, photocurability is the main requirement you have to be processed via wet photopolymerization base. It can be SLA or it can be DLP. Again, so here, this one, like tablet-like shapes, 3D printed. Here also like dental materials. All are research-based papers I have right used here to show you the capability of the technique, right? Then I will switch my gears to the powder-based fusion one, selective laser sintering, right? So this is where you use like materials like ceramic, right, and so on. So you have the powder, right? So there's a mechanism to introduce the powder to the bed, right? And then you can see selective laser sintering. So you are using a laser. Sintering means you fuse them together, right? You use laser. You expose the first layer to laser, right? Again, the laser traces the pattern, right? So in the wet photopolymerization, the cross-linking happens. Here, laser introduces heat, and then fusion happens, right? particle size is very important in this case, because you are using powders, right? So those are the technical or processing parameters. They have to, each and every technique you have to use the optimum conditions. Or those are all trial and error, right? You have to do many things to come up with smooth, to find out the smooth spot, right, for efficient printing, right? So that is the mechanism, right? Layer by layer again. So once the first layer is fused, then the next one comes, same thing happens, and then again layer by layer fabrication of the ceramic material here, right? Right. So again, materials like not only like PPS, sulfone, right? And polyethylene, peak, the ketones, and even metals, right? I told you, even metal powders. We have to have the powder form in each of these cases, right? To be able to use this selective laser sintering method, right? Then again, another sub-technique of the same thing, electron beam melting. So here, rather than using laser, what are you using? High electron beam, high energy electron beam, right? You can see a lot of metals and alloys being printed. Like, have you seen the biomedical implants, like the bone scaffolds, right? You can use alloys like nitinol, nickel titanium alloy, nitinol, right? Just for an example, I told you. And some examples here, titanium, aluminum, vanadium alloy brackets, you can see. So that's the example given in the slide. Alloy means mixture of metals, right? That's, right? Direct, like isolated metals, or in terms of mixtures, or we call that alloys. You can use for 3D fabrication via electron beam melting, right? So again, the technique, you use this powder form, right? Again, the powder layer, rather than using laser here, you use high electron beam, high electron energy beam. So you use them together, right? Actually melt them together. You have to, these are metals, right? So you have to have very high metals have very high melting points, right? So you have to have high energy. That's why you use electron beam, high energy electron beam. So that's why, again, based on the type of material, you have to change the mechanism, and you end up with a different 3D printing technique, right? So again, a lot of biomedical materials, especially I told you for the bone implants, and so I have slides I will go through. So they use EBM, right, to 3D print them, right? So some of the other some other materials here, and also there's another one, direct metal laser sintering, is much similar to the previous one. Direct metal laser sintering, same idea, right? Here, rather than using electron beam, it's again laser, right? Direct laser is used, right? Again, alloys and metals. You can see these are commercial numbers, right? 625 Inconel 620. Those are commercial names of these alloys and stuff. Stainless steel, titanium, aluminum, vanadium alloy, right? So those are mostly used for the biomedical, and you can see dental implants and prostheses, medical prostheses, right? This now the jetting techniques. You can see I have some taken both together, binder and material jetting, binder jetting and material jetting, right? So again, right. So I told you, in binder jetting you use an adhesive as the binder. In material jetting, right, you can see. So you have the materials comes, right, as right drops, right, droplets, and then you have to simultaneously cure them. So that is your rigidity enabling mechanism, UV curing, right? So we'll go through some other examples as well. So like materials like mostly like again ceramic, metals, alloys, polycarbonate, ABS, right? Going through this binder jetting, right? Binder jetting, again, you can see it's a human skull 3D printed using the binder jetting technique, right? Recently, because we are my postdoc group, one of the scientists, right? Emily Wills, she carried out this kind of work, right? So you can see processes and so on. So many applications, biomedical applications are there with jetting based printing. right? Direct energy deposition, you also call that DED, right? This is another version where a lot of metals can. There are two modes of DED based printing: coaxial feeding and off-axis feeding. Right here also you can see the metals. You are introducing them as powders, and again laser beams. You can use like coaxial mode or like at an angle, right? Off-axis, right? The similar idea as before. You know, layer by layer, you melt them together, right? One layer and the next layer, and so on. Lot of like stainless steel, titanium based, right? Cobalt based, nickel based, right? Shape memory materials. So I'll come to the shape memory stuff that is actually related to the 4D printing, right? Titanium, tungsten, ceramic. So again, lot of metal based printing via DED, right? Okay, so prototyping, you can see a lot of these are images of, right, the things that I kind of like summarizing things that I have gone through so far. Applications, like you can see here the processes for hand, right? Okay, now we directly come into the biomedical thing. Implants and processes, you can see, right? You can 3D print, right? Tissue engineering is another area. Drug delivery, surgical and diagnostic tools. So we'll mainly highlight these one, right? With these for actually processes, tissue engineering, drug delivery, surgical and diagnostic tools in terms of the biomedical engineering applications of 3D printing, right? Right. So I told you about the right, the bone implants. You can see there's like inside. You can see the bone anatomy, and you can see for the this is the human right, bone anatomy. Here you can see there are several places that right, that people have done research. You can see radial head prosthesis, right? That's for the arm, right? The porous scaffold in femoral defects. That's again, femoral means that's a leg, right? So here the upper part, people have researched and come up with 3D printed stuff, right? Material. And when it comes to the foot, right? You can see talus implant. Talus, it's in your foot, right? So it's a big bone, right? So there are implants for that. Now, all are 3D printed examples, right? That you can use for the replacement. Let's say you have a fracture in this particular place, fracture, right? You end up with a severe accident, right? So now the medical industry, together with additive manufacturing, they have come up with advanced materials like these things that now they have tested, right? These things outside, as I told you. So they have, you have to have the biocompatibility because you are using this inside the human being, right? So the surrounding tissues need to grow around these things without any issue, right? So you have to first test them, and then once they become successful only, then you apply. So these are successful cases. So luckily, so now that is why people are moving with the biomedical 3D printing materials, right? And also you can see spine fusion devices for the spinal cord here. That's close to your neck, right? The neck area, spine fusion device here. Then trabecular acetabular cups, right? That's again for this pelvis area, and also for the cones in total knee. Right here also there are a lot of knee replacement, the knee bone replacement because of the accidents can happen. Cones in total knee arthroplasty, right? So all these are right metal-based 3D printing, either direct energy deposition or electron beam melting, right? So there are several 3D printing techniques I told you that are capable of printing these type of metal-based structures, right? Okay, implants and prosthetics, right? Right. So now, so all these are like research-based images. You can see left-hand side the SCM, right? Scan electron microscopic images of a porous channel dental implants, right? In the middle, you can see polylactic acid. That's the left-hand side as the control, and they have mixed with this with the medicine, right? Antibiotic, PLA, gentamicin antibiotic. So this is the right-hand side. This is their sample. So they have used this for fixation screws, right? Interference fixation screws, right, inside the body, right? So all these are biocompatible. That is why you have the ability to use inside human tissues, right? So you can see these are FDM 3D printed. That's why I told you, you first have to have an idea about the 3D printing technology and the type of material that you are using. Right? You can see, right? The leftmost, it is DMLS. That's the that is what the wet photopolymerization based on, right? And middle one FDM, filament based one, and again the sorry, the leftmost one, direct metal laser sintering, using the laser beams. Middle is the filament based one, right? And rightmost again filament FDM, fuse deposition modeling. So you have, they have 3D printed, they have printed skull structure. Say human skull in red color, you can see the human skull, and porous implants in brown color. There you use the polymer, polyether ketone as an implant, right? Right. So you can use this for the damage or whatever the parts in the skull, right? Right. Next is the tissue engineering, right? Many, right, 3D, 4D printing, biomedical materials based on tissue engineering. So what you do basically, right? So most of the tissue engineering applications are DIW 3D printed. I told you that's the you fill all the material to a syringe, and then through the pneumatic pressure you deposit with the viable cells, the active cells, and then you have to do the trials to make sure the surrounding tissues are gone without any issue, right? So such successful research I have summarized here. You can see alginate silk fibrion scaffolds, right? So a lot of like wound healing applications, right? Right, and many other tissue-based applications inside the body, right? They are used these 3D printed materials. Again, the dental industry, dentistry, right? Right. So that is even in Sri Lanka now. Dental doctors are right. They have a curiosity of by doing the 3D printing stuff. You can see for drug delivery applications, you can see polylactic acid, polyvinyl alcohol-based mouth guard. Leftmost, you can see that is FDM 3D printed, because these are thermoplastic materials, right? So in the middle, you can see again this is mouth guard. With you can see some areas, some regions, right, where you can see these types of food flavor loaded and free regions. Right hand side, you can see right, model drug loaded and free regions. Now you can load the drugs, right, and then use these materials. All are biocompatible, and these are successful research for the dental industry, right? So again, control drug release shell, left hand side you can see without the cap, and loaded drug for the delivery, right? And loaded drug for the delivery. So right hand side, right? So these are drug delivery based applications. When it comes to surgical and diagnostic tools, right? Again, right, super porous hydrogel wound dressings, right? This is 3D printed via FDM, right? And also you can see 3D printed device for magnetic focus lateral flow sensors, like sensor housing, right? Again, you can use for this biomedical industry, right? To come up with housing devices, right? Right. So I think I have talked many about 3D printing, right? You can shift the gears to 4D printing. Actually, less number of examples for the 4D printing, but that is the advancement of the 3D printing. What is the fourth dimension, right? That is the time-wise changing, or you can say due to a stimulus like temperature, it can be a pH change, it can be a light attraction or magnetic field. All these are stimuli. You first 3D print the material, and you are exposing the already printed material to either one of those stimulations that I told you, one or more than one, right? If it reacts to more than one, it is very versatile, right? Especially in the biomedical field, right? Because in the human body, there are a lot of changes happening, right? Okay, this is the next generation advancement, right? So this is the 4D printing. So you get the 3D printed object, you change the pH of the environment slightly, and then the material responses to that change. So it can be a shape change, usually functional change or shape change. So imagine that you have a 3D printed material, and with temperature, slight change of the temperature, material changes the shape, maybe to a gripper system. So that's very directly useful for the biomedical surgical tool, right? I hope you can get the idea, right? And you can, suppose you have a material 3D printed, and you change the pH of the medium slightly, and it responses. And that can be directly, if it works, right? Maybe a functional change. If it happens, then you can use it for the human gut, right? Because like there's the place where the pH changes, right, in human body. So I'm just giving you some examples and the application that we have to check for when you are using in the biomedical field, right? So this is the kind of idea. So the image actually has you can see the shape changing, right? With time, you can see seconds and the shape changes. This is actually due to temperature change. So I will show you many some of the other examples. Here's the summary of, you can see pH responsive, electro-responsive, moisture responsive, thermo, photo, magneto, and mechanical stress. So you can see more than one stimuli here. Most of the materials up to now that have been successful for the biomedical, those can be denoted as thermoresponsive and pH, right? Most of the things so far, thermo and pH, right? Some and also photoresponsive, right? Now people are searching through these mechanical stress responsive, magneto, and so on, right? Because every day you need a progression, right, of the science, right? Now, having said that, I will directly move to the next slide. Right now, you have the basic idea now. So the same idea shows here. You have the smart material, right? Smart material means the material has the ability, right, to respond to external stimuli. That is why it's smart. And also it has smart materials have some one category have the memory, right? That it has the memory, the initial memory or the initial structure. It can change to a temporary structure but come back to the original. That's called smart materials, right? So that materials have those, the material, that's the characteristic of the material. So if you use such material to 3D print, so you can come up with the 4D printed structure, because such material responds to the external stimuli, right? So the same idea I have illustrated here in this slide, right? So I will move forward because I have few minutes, right? Okay, so next one, yeah, the history. I told you, 2013 actually. Yeah, they you can see introduction of 4D printed uh, objects. Skylar Tibbets, that's the researcher. That's the researcher who did the pioneering work for 4D printing, self-folding structures, 2013. And then you can see it's a development, right? Then you can see hydrogels printing with thermal stimulus, right? And then you can see 2016, 15 4D bioprinting, right? So I told you about bioprinting, and if the material responds to external stimuli, it is 4D bioprinting, right? If you can do it like 3D, it's 3D bioprinting. If the printed material responds to the external stimuli, that is 4D bioprinting. Hope you get the idea. right? And also people came up with 4D nano printing, right? Self-healing materials, then multi-material 4D printing. In this multi-material, that is like you deliver more than one material simultaneously. This is right. Also in 3D, that multi-material 3D printing, right? And if it responds to our external stimuli, then it comes multi-material 4D printing. So you have to have more than one nozzle, like co-axis, right? Co-printing, right? At the same time, you deliver more than one material. So it is a very versatile technique. You cannot apply this every time. So you have the materials, the range is limited. So this is where people have to look for such kind of material, because you can get many, properties like the multi-material. No, one can respond to temperature, right? Another can respond to pH, right? You see the point I am talking about here, right? If people can come up with good multi-material 4D printing, it will be very highly advantageous in next generation biomedical printing, right? So 2020, you can see 4D printing entirely resourceable scaffolds, right? So it's just growing up, right? So now you have an idea. Right now, some of the examples I wanted to show you here: moisture sensitive hydrogels, right? Using direct ink-write printing, right? So people have come up with such hydrogels. Usually these are for tissue engineering applications. And then thermoresponsive, you can see that the top image, you can see uh, right, these materials, right, they change their shape. Usually what you do is like you have to have an idea about the glass transition temperature, right? That is where this most of the polymer stuff they want, right? The starting point there where they try to move, right? You start from a solid material, then you heat the material, right? At some point it starts flowing, right? That's the glass transition. Then actually you have to heat the material above the glass transition, and then you can fix the shape. That's the temporary shape. And then upon cooling the material, you can get the original, right, with time, right? You can get to the different shapes, right, to the function you need. That's the that's the advantage of right, these kind of smart materials, right? You can see shape memory effect and also shape change effect, right? Two slightly different things, but right, both are very applicable in 4D printing, right? So you can see the gripper system right now. I'm applying this right here to the surgical and diagnostic tools. Now you can see the system when it's in open mode, the left hand side, right? So then let's say you change the temperature and the gripper closes, right? Then you can grab the object, that particular thing can grab the object, and then you can deliver it to somewhere else and drop again, right? Just by slight changing of temperature, right? So those are the medical applications, right? If you can come up with such materials, right? Using right single material or multi-material, that is the way to go, right? That is you can do a drastic change to the medical industry and also to the dental industry, right? So thermoresponsive, many applications are here, especially very versatile for bioprinting, biomedical materials. You can see many printing methods are also available for this. FDM, SLA, you can see right here, DIW, jetting, right? Then photo or light responsive. Here, light actually it's an indirect stimulus. Why? Because you expose the material first to light source, and then light generates heat. Heat does the shape change. So that is why light is an indirect stimulus, right? So people have used SLA, right? Stereolithography, right? That's the laser-based technique to 4D print such materials, and also electroresponsive. Electroresponsive, you expose the material to electric current, right? It's an indirect stimulus because when it passes the electric current through the material, it generates heat, and heat does the shape change. So that's why again electricity has become an indirect stimulus. Such materials are also have been printed using SLA, stereolithography, right? Some images I have used here. In magnetoresponsive, with time, it's also changed the shape because of the magnetic field exposure, right? pH responsiveness, right? As I told you again, if you could come up with such materials, right, successfully 4D printed, then very useful in the gut area or like a relevant area. I mean, in the human digestive system. Let's say if something happens to a particular person due to accident or something, then if you have a successfully 4D printed material, right, through research you have used, so you can directly replace that, right? It has to have the time-wise, you know, uh, recoverability and time-wise, right? You, storability and those things, right? Those are the challenges, right? So that is where research needs to go. That is the idea here. So again, many applications. If you come up with pH responsive 4D printing with drug delivery, not only biomedical field but in robotics, actuators, like lot of mechanical engineering actuators, valves, biocatalysis, and so on, right? Piezoelectrics. If you use a mechanical stress, right, then that is the, for such materials, mechanical stress is the stimulus, and then the shape changes occurs, right? DIW again has used, right, has been reported successful 3D printable method for piezoelectrics, right? So we went through a lot of biomedical engineering examples and 3D and also 4D printing techniques. You can see not only biomedical but also robotics, like origami, like right, and some other, again, biomedical 4D printing biomedical applications. You can see the images. This is summarized in a recent review done by myself. And, these are directly from research papers. You can see 2023, very recently published, right? Like T-junctions, tissue scaffolds, like tissue conduit. Like you can see the like a cylinder shaped things you can use for drug delivery, right? Inside human tissues, right? And again, smart vascular conduit. Again, like conduit means a cylinder shaped thing you can use for implants and prosthetics, right? Surgical and diagnostic, like gripper systems, right? That these things I already discussed. These are recently published 4D printed biomedical, direct biomedical materials. Other applications, as I told you, origami, that's like, the like the origami field, right? There you need the mechanical stress and temperature responsive materials, right? The idea here is not only biomedical, you have myriad other applying places for 3D and 4D, flexible electronics, soft robotics, because every time you have the right 3D printed material, right? That's complex shapes already. You have come up with the complex shape, and then with the external stimulus, exposure to external stimulus, then there's the shape change or functional change. That's the other advantage. So you can see whole lot of applications there. This is a summary slide. The things I summarized so far. You can see the tissue engineering, surgical, implants, and drug delivery, both 3D and 4D examples. Challenges, yeah, you have to have proper material, right? You have to have the proper viscosity, right? Proper mechanical strength, right? So far, they have low mechanical properties, right? Low biocompatibility, but these are the challenges, hurdles that researchers are experiencing, right? So you have to break these hurdles and move forward, right? With daily searching, with your curiosity, right? The limitations we have in Sri Lanka actually is the financial potential people have, researchers have, right? But we can have good collaborations with our other countries, and that is where everyone has to. That is why I appreciate this kind of seminars and this kind of like networks we have to build up among the scientists we have in Sri Lanka, and we have to do something. We have to think. We have to plan for future development of materials, right? 4D printing needs further improvements like stimuli responsive, right, and so on. Future perspectives, novel material design. We have to think about the safety, biocompatibility, precision, and functional effectiveness, of course. And multi-material. This is the thing I told you. If you can come up with these things, this is the way to go in future. You can have many advantages in a relatively short period of time by using multi-material for the printability. And also you have to have development guidelines, you have to have regulatory guidelines, licensing, quality control, technical. So you have to have idea about these things also because you are dealing with the biomedical field, right? And just a couple of words for about 5D and 6D. So not only 3D and 4D, people now research for 5D, that's again rotational axis. You have the X, Y, and Z, that's the 3D. How about rotating, printing head and print bed? If you could rotate those two, then it's 5D, 2 dimensions with the rotation. What's the advantage? You can print like very complex, like curved shapes, right? It's advantage for in the biomedical sector, like curved shapes, like bone implants and so on, like a curved surface. No? What is the 6D then? So if you have the 5D, right, then if it becomes functional with time, that is 6D. Okay, that's the idea. You have the 5D thing. So you have to have one more addition of dimension. That is the time-wise or the same thing like 3D. That is the 4D is the advancement of 3D, right? That's the 4D time-wise response. Now you have the 5D. This is kind of like 3D, right? 5D. You have the rotational axis, right? Then if the such material responds to those stimuli, then it becomes a 6D printable material. Right. So if you could come up with such materials in future, we hope we could do something in future as Sri Lankans, right? So we have to move forward, right? That's my idea to the scientists around me. Thank you so much again for giving me the opportunity and some of the references. And again, I appreciate this opportunity. It's open for discussion.
Thank you so much, Dr. Sirivardhana. Very valuable session. And so I think this session is very important for us because nowadays everyone talking about this 3D printing, 4D printing, and your session is very important. And you introduce us various 3D printing mechanisms.
Thank you.
And it's very interesting. And I would like to invite our participant to ask questions from Dr. Sirivardhana. So now the session is open for the discussion.
Thank you, Dr. Suranga.
Hello, Dr. Sirivardhana. So I have a question actually. So when you discuss about these various printing techniques, those are called techniques, right?
Yeah.
So the film, can you go to that slide?
Sure.
You introduced several.
You are talking about the
Yeah,
initial.
the film. Yeah, the initial one. Yeah, that 3D printing. Yeah, that was that one. Yeah. So now I know that FFF. So but now when we think about the practical situation,
Right.
are there any machineries available in the market for us to purchase and start a business, something like that? For an example, if I want to do a printing for example, think I want to print a bone.
Right.
So, are there any machineries available, the 3D printers available in the market to do such level of initiation?
Yes, Dr. Surang, it's a good question and a good practical question. Right now, we have in Sri Lanka actually you can buy like like a 3D printer, like filament based 3D printer for 1.5 lakhs. Like 15. It's 1.5 million, right? 1.5 million. You can buy
Okay.
3D printing machine, right? No problem with that. So right, with the specifications and help like tool kits and so on. So you can buy, right? So yeah, we have the capability of purchasing such, and then we can do the printing. No issue with that. We have the compatible nozzles, and usually like like 4 and 0.6, and so like copper based, right? So nozzles are available. The technique is there.
Okay.
Machines are available. Yeah, no issue.
Yeah. Thank you.
And
Doctor,
actually, we can use
may I ask
we
a
can
question?
manually build the DIW. We can manually build the DIW one, like even for the like then
Okay. Okay. Then.
yeah, making cakes like icing. That's the
Mhm.
DIY one.
Okay. Mr. Jayatilak, yes, sir. Yeah.
Yeah, my question is are there any manufacturers in Sri Lanka presently uh, using this technology?
Manufacturers. So actually, we are purchasing from countries like uh, India and China. Actually, we have people right that actually I know some people actually like some people was my students, right? Right. So like they do a lot of like repairing and that kind of stuff now. Like there are places in Sri Lanka that they do quite a lot of this filament based printing. Yeah, and they have the repair centers as well. Yeah.
Because this is
Currently, yeah,
you are focused in uh,
yeah,
uh,
bio printing. Yeah,
bio yeah. Now I know during surgery sometimes
mm,
the doctors have to get down certain parts of the bones and so on.
right. That's true. Yes, sir. Am I audible?
Yeah. Yeah. Yeah.
Yeah, yeah, yeah. Actually, that's a good question. Right now, that's the future thing we have to right. We have to think about like doing the like applying this 4D printing materials with the like simulation with like real time monitoring, right? With real time monitoring, if you do a surgery or that kind of thing, yeah. So that section needs to be improved further, right? Yeah. So like people are actually no, in the right in Europe and US, right now they are looking toward that one 4D printable materials like like operates with real time monitoring and so on.
Is it being used uh, commonly in Sri Lanka in the
So like
medical field?
not in Sri Lanka though, but because in dental industry, I heard like a couple of weeks ago now dentists are having the curiosity of using, like the challenge they have is the allergic reactions coming up, right? Because if the material is not biocompatible, sir, then like side effects, right? Allergic reactions occur, right?
Yeah.
Now, yeah, so that's the thing. Now in Sri Lanka, the curiosity is there, but we have to come up with such good compatible materials for the dental field because like now the dental doctors in Sri Lanka they are curious about because like other countries they do like a lot of these dental implants, that mouth guard and so much things, right? So many things, but in Sri Lanka we have to there's no such successful things that much because like you have to do that like bioprinting. Successful bioprinting has to be done first, yeah, with techniques like DIW or ink based, yeah.
Yeah, according to my
Mhm.
understanding
Ah,
now, replacement of knee is a very common thing in Australia.
right,
Uh, in the slightest thing, they
yeah,
replace the knee.
right,
Now,
yes, yes,
do they manufacture there? Do they manufacture these things in Australia? Or
yeah, even in US and other countries, yeah, they do, yeah, they do. I mean that's why, so you have the that's all based on metal, no, metal based the knee guards and so on. You have to have high temperature processing all those metal 3D printing like high electron beam, or it can be laser sintered direct metal laser sintered DMLS. So you have to have high capital cost, right? So such countries where they have the financial capacity, they do. Yeah. Actually, that's why even in Germany, right? So that's why they publish papers and they actually need other scientists to, like work on those things, right? So yeah.
Has any attempt been made in even at university level to try and introduce even in a small scale some
Mm,
manufacturing?
right. So actually, to be honest with you, like my research group is targeting for such kind of things. So far, I mean, according to my knowledge, not that much high successful things so far, but yeah. So that is why that gap has to be filled. Yeah, that research gap is there because like so far also we have the filament based one in Sri Lanka. No, those are usually used for like household printing and some like replacement of like some machineries. Some you can 3D print like the rotating screw part and use. So such kind of things are being done, right? And that and others like demonstrating like prototypes, right? But not that this kind of like hardcore medical stuff yet. But now the medical doctors and even dentists are having curiosity, right? Yeah, we have to go through discussions actually, right? Yeah. The only hurdle is the money, the funding for the
Mhm.
technique and the material. Yeah, I mean honestly, even in my Dr. Suranga knows this. Even in our labs, right? We do very low. I mean, actually zero synthesis. No, I mean, am I correct, Dr. Suranga? Synthesis wise, we don't have we have the knowledge, right? But we don't have the characterization things. I mean, once you do the synthesis, you have to purify the product and come up with the material, right? So you have to do many characterization things to come up with a good, acceptable final material, right? That is why a lot of like wet photopolymerization with new materials. You have to, I mean, you have the commercial material, but that's not the research. No, we have to think about synthesizing new stuff. No, that's why we are doing a lot of like composite based materials, right now, right? Because we don't have the characterization facilities. Even well, we have to do it even through India or right China, but they cost a lot. Am I correct, Dr. Suranga?
Yeah, what is the cost of the polypropylene 3D printing filament per kilo?
Polypropylene filaments are there, no issue. PLA is like
Yeah, it's
one
cost about 18,000 rupees or something like that, right? That's another.
polypropylene 1 kilo. One
Yeah.
that filament based one around not that much because like even PLA is like 5,000 one
Mm.
kilo, right?
That's another business area actually.
Yeah, that's true.
Creating raw material for 3D printing industry. So that's
Right.
another.
Yeah, yeah.
Yeah,
That
so I just went through some videos in YouTube and just found a
mm,
video related to the this one of the technique you have discussed. So this one, this is the one you mentioned about
yes,
that
DIW. Yeah, yeah.
DIW,
Uh-huh.
DIW, right? So now this technique is just a slurry. Uh,
Yes.
s-
And the pressure, pneumatic pressure from the top.
yeah, yeah. Just so the slurry is carefully poured. Now it's
Mm,
like a CNC machine, right? So
yes,
the
yes,
design is fed to the computer system, and then
right.
the nozzle is moving to develop that pattern, right?
Exactly. That's a good point. So now you will ask me how this is a slurry, no? This is a
Yeah,
hydrogen or a paste. So uh, what is the mechanism to make it rigid once you print it, right?
yeah,
So you have to simultaneously expose this to UV curing. Okay. So this
yeah.
kind of material either should have the UV curability or have to have the viscosity-wise robustness itself. Right? Most of the time, you use a UV curing simultaneously, but you have to be careful. If you cure the material inside the nozzle, what would happen? The material flow will block, right? So you got the point, Nick?
Yeah.
Right.
So these kind of printers, are they available in Sri Lanka? Is anyone using currently? It's very curious because now, yes, the PVC, we can make a slurry similar to like that.
Right. So not that I
Yeah.
know, but you can direct. Yeah, actually, we have the digital pen. Have you seen the digital 3D pen? So that has this mechanism. Yeah, pens are available, commercially available pen. Right? It's a like a cake icing thing. You can use that pen, but that's a very fancy device, right? But we have not that I know of, people those who are doing 3D printing, they use the filament based one.
Yeah,
And
that's the most popular one. Yeah.
then now several places they use the laser based machine, the SLA one, SLA resin based one, basic one. That is
No.
also capable like 2 lakhs in LKR. That's also, but the thing is like they are also using the commercial acrylate based resin. They just print the high resolution stuff, and then they kind of like use for the exhibitions to demonstrations, such things, right? This is a good point. Actually, we have to seek for the places where you can buy DIW. It should not cost that much. Even people can manually build, right? It's a syringe. Top, you have to apply the pressure. Underneath you have the nozzle, needle like nozzle.
What are the common products? Things like heart stents and uh, sort of
Sorry, sir.
cataract lenses. Are they made with this technology?
Like DIW one, the
Yeah.
one that,
Say, for
yeah,
instance, cataract lenses. Do they use this technique?
yeah. Most of the things like tissue scaffolds, like for the tissue engineering applications, like that's the bioprinting, no. In yeah, like device wise, mostly used like in Sri Lanka, they use the thermoplastic based materials. But yeah, in countries like Europe and US, yeah, they do. Even they have even 3D printed lung structures, right? And that like parts for nose, right? Parts for nose and ear, right? Using the bioprinting. Yeah.
Mhm.
Ear replacement parts for ear, right? Because for an example, if something happens to your ear when you
Mm.
travel, especially through
Yeah.
bikes, right? They have printed like all those high resolution, all those things go through this SLA, the selective laser SLA, stereolithography. Yeah, they have ear parts, parts of the face, parts of the nose, yeah, and also inside body parts. They do. Yeah, actually, that's something we
Okay.
have to, yeah, scientists and medical doctors will have to, like have some discussions like this, and we have to little by little, yeah, progress our research to this field, right? Yeah.
Yeah. Okay, Dr. Sirivardhana, thank you so much. Are there any questions from the audience? So if not, we can conclude the session. Thank you so much, Dr. Sirivardhana, again,
Sure,
for your
sure. Thank you
valuable
very much.
time and educating us related to the 3D printing technology.
Yeah, sure.
Thank you so much.
I look forward to join with you in future too. Yeah, just thank you
Thank
again
you, thank
for
you,
having
thank
this.
you. And I would like to pay my gratitude for all the participants today, especially Mr. Anand Jayatilaka. I especially invite him. He's one of the pioneers in Sri Lankan rubber industries. And all the participants, thank you so much joining with us for this PRI webinar series. And we have already scheduled series of webinars, 2 per month, and we have it's a our webinar is very short, usually 1 hour, maximum 1 hour. But if you feel like that you need to have more time related to specific topic, then you can send that request to our Mr. Chaminda at PRI, Director General, and he will arrange a special session for related to the specific topic. If our audience, if our members interested in having a in-depth discussion related to any specific topic, we can have a different session later in the year. Then you all can have in-depth access to the knowledge of our speakers. So thank you so much again. Thank you so much, Dr. Sirivardhana.